Just before I get started on this, how many people how many of you have heard of Esri as a company? One or two of you, maybe three. Esri stands for the Environmental Systems Research Institute. It's a US-based company, and I'm not going to give a standard marketing pitch on it, but it's the world's largest producer and supplier of geographic information systems software. So people ask me to make an analogy. Esri to GIS is somewhat like Microsoft to operating systems and to desktop productivity. So it's a very large company, and Esri Canada is a Canadian-owned company that's a branch of Esri's international family of companies. We basically distribute Esri software in Canada and provide value-added components to it. My role as Director of Education and Research in the company, I'm responsible for the use of the technology right across the education system, from kindergarten all the way through to postdocs and to faculty-based research. That's a broad spectrum. But essentially we focus on university-based work, and that's what really has spawned this relationship with James and Gun Ho here at York and other colleagues as well. I should note also that I'm speaking on behalf of two of my staff, Michael Lubert and David Kosowski. They're actually the two guys who have done most of the work, and I'm really just the messenger and the director of traffic. So what I am going to talk about is really a good extension of Gun Ho's presentation, and it's focused on the development of an immersive 3D model for York University's campus that we plan on using in a research project, a multi-year project that James is principal investigator of, and that's focused on this campus and the surrounding area. So we didn't only build it for that purpose. We built this model basically to help us learn some of our own software. So there's a heavy focus on the use of City Engine, which is Esri's 3D procedural city modeling software tool. And I say procedural because the software is built around the idea of generative grammars that are rule-based. And so it's procedural in the sense you can fire procedural rules and construct individual dwellings and expanding out whole cities, including not only buildings, but also other attributes of the human and physical environment. So everything has to have a beginning or a starting point. And so the York model, I've termed this slide Genesis, because it stems really from a similar model that we built at the University of Waterloo. And James noted my history with Waterloo. It was an appropriate place to start in terms of working with City Engine to learn it and to see what we could essentially do with it. As part of this initial work, we were working with a company that we'd invested in, a startup from Waterloo. Thanks, James. Yeah. We were working with a company that was a startup from Waterloo called Mapped In, and their business function and business market was focused on large indoor complexes like shopping malls or airports, university campuses, and constructing 2- and semi-three-dimensional plans of the interior of these facilities and building out routing apps so you could find your way from one part of a large facility to another. And we wanted to see how well City Engine would do in that context and how well we could build out indoor routing as well as outdoor routing in large facilities using Esri software. So we started to experiment with City Engine, and we've integrated it with Unity. So before we get to the York model, I just want to show you very quickly a couple of examples of some of the work we did at the University of Waterloo. On the your right over here is a native iOS application written in Objective-C that allows a user with the University of Waterloo's campus to find a room on campus. It's a very simple app. You enter a room number, the app goes off to a server-based service that identifies the location of the room that's coded into each of the floors that are raster scanned images for every building on campus, and it shows you the location of the room and tells you exactly which building it's in, and that allows you to navigate without any routing information fairly quickly. Going beyond just simply finding rooms, you need to know how to get there. So we wrote a second app that allows you to navigate, again, a native iOS app that could easily be rewritten in Java for Android devices. It takes you from the point that you start at to the point that you want to get to using both 2- and 3-dimensional routing to get there. So if you have to navigate between floors of a building like this, if we were starting in this room, the route would go out the door to the elevator, we'd go down in the elevator, and as we move between floors, the floor plan would change according to the level that we're on. And then we can navigate the path with the slider at the bottom of the device that gives us information about where we go next. And we can also set this route so that it optimizes the amount of indoor navigation we have to do if it's cold in the winter. We don't want to go outside. We can use tunnels, or if we want to have a nice walk, we can set it to go outdoors. And then going beyond that, we have the 3-dimensional world of the campus. And this is where we move from City Engine into a gaming engine you may have heard of called Unity. And let's just hope that this thing, you know what, it's not going to run. It's a pecker. But maybe it'll run on your devices if you all get access to this PowerPoint presentation. And this takes you on an immersive walk through the campus during the day and at night, so you can see how we can modify interior environments in terms of lighting and also outdoor lighting as somebody navigates around the campus when the light conditions change. So that was genesis of our work. We wanted to do some experimentation with the University of Waterloo, and then take what we'd learned from that and start to work with York University's campus to see what we could produce for the work that we have planned with James and Gun Ho. So in the presentation today, I'm quickly going to step you through the workflow that we followed to move from some initial constructs, process them using a variety of software platforms, and ended up with a really nice semi-immersive model for York University's campus. It's a work in progress. It's not finished yet. And given that the first video didn't work, I doubt whether the last video is going to either, but hopefully you'll be able to play these yourself. So I'm going to step you through the process that you see on the slide behind me. So, oh, okay, good. Maybe we can just show them at the end. So given that we started with Genesis, we're now moving to Exodus, and this is the point of departure for our work on the York campus. Gun Ho mentioned in his presentation a model that was developed by him and his students and James 7 years ago. And this was that model. So that's the point that we started from. And we wanted to take this model to enhance it where we could, to modernize it, to remove buildings from it that were no longer present on campus, and to add some more detailed buildings into it, as well as other characteristics that bring the campus to life. And we wanted to do this in the context of this, primarily this software platform, Esri's 3D modeling platform. So the initial model from York, the geometry of it was very clean, and the buildings were relatively accurate, which was good. But the textures that had been mapped to the building had many non-facade elements in them. They had trees and other characteristics that were mapped onto the facades of the buildings, which we wanted to eventually get rid of. Some of the textures were mapped onto incorrect faces, and we wanted to tidy that up a bit. And given that the model was 7 years old, as you can see around you, there's a lot of construction on campus. We wanted to move the buildings that were no longer there out and add much more detailed buildings in. So to do that, it kicked off a multi-part workflow. And so if you're thinking of building models like this using multiple environments, you have to be prepared to be a little bit nimble and work with many different software packages and eventually pull them all together in a common environment. So that's what we're going to step through for the next few slides. One thing that characterizes our model that you'll see, which is very nice, is that we have a number of building information models that are part of the overall master model. A building information model is typically produced by an architect. It contains not only the geometries of the building that the architect's designing, but all of the parametric attributes that relate to characteristics of the building, including furniture, light placements and light characteristics, building materials such as the exterior construction material of the building and the interior construction materials of the floors and so on. And BIM models tend to be highly complex and very specialized in terms of the environments they live in, which are typically CAD-oriented environments. So step number one is we were lucky in the sense that we established a good relationship with facilities management here at York, and they gave us 5 BIM models to start to experiment with and see how easy it would be to take those BIM models and translate them into an environment that we could work with. So that's step number one. The format that the BIM models arrived in, and these are based around something that's called industry foundation classes. They can have varying levels of complexity. These models have a level of detail, 5, which is one of the highest levels of detail that a BIM model can carry with it. And given that they were developed in Revit, which is AutoCAD's BIM environment, we had to move them from Revit into an environment, into a format that we could read into City Engine. So initially we converted the 2005 Revit files to Revit 2017 format, which is what we were using. We isolated the interior and the exterior of the buildings, so we could just include the shells of the buildings, but also if we wanted to include the interior construction and detail of each of the buildings. And then we exported those to Collada so that we could import them, Collada format, so we could import them into City Engine. So it's a simple process, but it actually required quite a lot of work. And this is the result of this process. Here is one of the buildings, and given that we're not in presentation mode, I can't remember the name of the building, but perhaps you guys could. You live at York, you don't know the building? That's not good. Anyway, it's one of the newer buildings on campus. And I just didn't write it down, so I can't remember what it is. This building here is, I think, is the parking garage that I parked in this morning, which is just across the road from us here. So that was the second BIM model that we had. I think this is life sciences, is that right? Yeah, so this is the life sciences building. And again, we have not only the exteriors, but also the interiors of these buildings modeled. And you can see around the building, we have the construction that came from the 7-year-old KML files that were built for Gunho's 3D Town project. This is the Pan Am Stadium, and as I said, we could differentiate between the exterior of the building, and as we peel that away, we can see the interior of the building right down to the level of individual desks and chairs, and there's much more information within that model than I'm showing, and I could show it in even more detailed information still. And finally, we have the building that we're in at the moment, and it's actually a fantastic building information model construction. And this is the exterior of the building. We peel that away. I actually think we're in one of these, maybe in one of these, I don't know where we are in the building, but we could find ourselves if we wanted to easily enough. So you can see the interior construction of the building, and of course we can move anywhere within that internal space that we want to. So that constituted step one, was getting the BIM content out of Revit into Collada and into City Engine so we could model it within this immersive environment. Secondly, we needed to create context and texture for the environment outside the buildings primarily. And we could do that in a couple of ways. I'll come to one of them in a second. But the first was to take a large AutoCAD file that facilities management had for not only all of the buildings on campus, but all of the trees, the street furniture, the light fixtures, the roads, the walkways, and so on. So we took that large and very, very complex and overly complex for our purposes AutoCAD file, and we needed to clean it up. So the steps we followed for this, first we selected the relevant components of the CAD file that we were interested in within Autodesk software, not in the GIS world at the moment. Remember, these Autodesk files have no knowledge about anything other than each line knows only that it's a line. It doesn't know what it's connected to, and it doesn't know where it is, either with respect to the building or with respect to the surrounding environment geographically. So we selected the data that we were interested in. We removed irrelevant line types and annotations, and there were many of those from the file. We closed polygons that were open, that we needed to be closed, that represented things like distinct land use types. We consolidated the data into a reorganized layer list that was relevant to us. Ran a couple of tools within Autodesk to tidy up things like curves and splines and convert them into polylines that Esri's desktop software could read. We then ran an explode overkill command to remove any duplicate line work and exported that out into a DWG or an Autodesk export format file, drawing file that we could read into Arcgis desktop. And so then we come to step number 3, and that's where the GIS world takes over from the CAD world. So here is where Esri's tools jump to life. And this is quite a complex flow here. I won't work through it in detail given the time that we're working with, but we took the file from AutoCAD. It was actually a DWG native file rather than a DXF export file. We georeferenced it, so it knew where it was on the Earth's surface. Did some further processing to identify land uses and land use types that we're interested in for the overall York model, so we could code these according to what exists on the ground, and we used aerial imagery to identify those land use classes. We then generated, in this process down here from contours, a TIN. Does anyone know what TIN stands for in here? It stands for Triangulated Irregular Network, and what it does is takes elevation points, triangulates those points. Each point has a value of the Z height of the point above the ground. The denser the tin, the more accurate the terrain. So we took contours, we generated points from the contour lines, built a tin from those points so that we had an initial terrain surface for the campus. We then intersected all of the land uses with the tin, so everything knew where it was on the surface of the Earth. Ran a process called tin to raster. So we moved the vector-based triangulated irregular network to a grid so that we could then produce a digital elevation model, which is a dense grid cell-based structure of the terrain that has a height associated with each pixel on the elevation mesh. And so at the end of this process, we had a texture-based map of land use classes, including roads and so on, and a very good elevation model that we could start to place everything onto. And I'll just quickly step through this. This is an intersection of the tin. You can see perhaps the triangles underlying the land use classes, and on top we have some land use classes identified, a parking lot, some other buildings, and that red square is roughly the area that the previous slide came from. We then had the land use classes that we'd coded from the CAD file and use of ortho imagery. We had light posts that we extracted from the AutoCAD file so we could create outdoor lighting and build models of the light fixtures outside on campus. And to add context to the model, we had all of the tree locations on the campus. So we're just about ready, but not quite. So we've got everything to the point where we want to get it to, which is into City Engine, Esri's 3D modelling environment. We have the stuff that we'd taken from the initial campus buildings of Gun Ho, information from the CAD file that we'd worked with. We had our BIM, Building Information Model buildings, and we had our elevations in a digital elevation model. So we then moved all of these things through to have some exported elevation values and an exported FBX model that we could then take from City Engine and read into Unity for doing further rendering and some animations. But we weren't quite there yet. We wanted to add detail to the model, and in particular, we wanted to run some rules that generated things like tennis courts, basketball courts, parking lot lines, the football field, and so on. So these pieces of the model were all built procedurally using CGA scripting. It's computer-generated architecture, which is the rule-based system that City Engine uses for construction. And you can see here I'm building a tennis net that's constructed of a court, a net, and a post at each end of the net to hold it up. So that's the rule set for building the tennis courts, essentially. And at the end of that, we have basketball courts, tennis courts, and the football field with posts and markings to add context to the model. So we're just about there. We're at the last step now, which is the model's in City Engine. We've added context to it. We now want to build that into Unity, the gaming engine, for animation and further detail on the model. So we take the elevation from City Engine, wrote a script in C# to build a terrain object for Unity. We took the FBX models, which is the output of the buildings and so on from City Engine, scaled those and inserted them into Unity. We took the terrain, wrote another C# script to do process that, and we ended up with the final Unity model. And so Genesis, Exodus, now we're at the Promised Land, which is the final model of the campus here at York University. And you can see the BIM models that we have in the scene. There's the Bergeron building, there's the parking garage. I think that's student life sciences or student sciences, life sciences, yep. And this other one that we don't have a name for yet. Somebody will tell me what it is eventually. You can see the trees on campus. We've got the Pan Am Stadium as well in the scene. So we have 5 BIM models included. We don't have any textures mapped to the buildings yet. That's a further stage of work where we want to do that texture mapping as well as we can, and that will really make this model jump to life. And if this machine worked, and it's not going to, but there's a video there that will take you on a fly through the model. We're not quite finished yet. One very quick point is that this BIM model inspired and City Engine created model that now sits in Unity is really just the start of the work that we're going to be doing with James and Faustos, whom you're going to be hearing from a little bit, Petros, sorry, whom you're going to be hearing from a little bit later today. In the sense that we now want to use this model to do things with it. In particular, we're interested in crowd management. How do people move around within buildings and move between buildings on the campus? And to do that, we're going to integrate our model with a software package called Steer Suite that models the behavior of individuals and crowds in 2- and 3-dimensional space. So that really represents the next step of our work. You can see these agents in the screen capture below in Steer Suite moving through. If this was animated, you would see these objects or these agents moving through the gap in the wall until everybody gets onto the other side. You can actually take Steer Suite outputs now and model and render these movements of people within 3-dimensional space using 3-dimensional avatars of individuals. And so that will really bring our model to life. And the other thing that you don't see in this, it's very inanimate. It's just buildings trees, things. There's no people. But we can insert people very quickly into this model. We can insert cars, we can insert TTC buses, and we can animate whatever we want within this gaming engine that we're now living in, with the model that was had a long development process, but now that it's there is a ton of stuff you can do with it. And I'm just going to leave you with this. I'm not going to talk in detail about it, but this is another way of bringing this information to live using web-based GIS. Just in the last month, we've developed an app using Esri's JavaScript API 4.2 that allows us to feed live data to the web within a three-dimensional environment. So this is a model of Toronto. This model has every building in the Greater Toronto area in 3D. This is the downtown part of the city here that we're looking at. This is also live, but I'll leave you to play around with this yourself. Do I have 2 minutes, James, or I'm done? Let's just... So this is now live on the web, and you'll see the buildings start to come in fairly soon. So this is a 3D web scene service of Toronto. There's the Queen's Park Triangle down around Harbourfront. The little agents that you can see hopping around the road is a live feed coming from the streets that have Bluetooth and Wi-Fi sensors on the streets that are monitoring traffic in real time. You can, if we click on the carousel at the bottom for traffic, you can see these purple identification points pop open. If I click on one of those, it'll tell us what the speed at that location is. It gives us a sense of how fast the traffic is moving, what's congested and what's moving well within this model. We can also click on all of the traffic cams within the City of Toronto. So if I want to go to a traffic cam, that'll show me what's happening at that point. This is updated every 5 minutes, live on the web. And remember, we've got the 3D buildings in the background here. So if we wanted to scroll up, and I won't show you this right now, but we actually do have York's campus in another version of this, the model that I just showed you. So actually, this is York's campus right here at the north end of the city. If we want to, we can choose a TTC bus route from this. What's Kiel, I think, is 196. I don't know whether 196. There it is there. So if I click on that, that's the route. And the buses actually move, these little white dots, that's real-time data coming from the TTC at the moment. And so if I click on one of the locations, it tells me how long the wait time is until the next bus arrives. The other thing that's nice about this is we added some data from Vision Zero. And this is of interest to the ISUM project. This is the location of every accident in Toronto since 2006 where there's been a fatality or a serious injury. So it gives us the time of day that this happened, the location, the nature of the accident. If we just click on randomly one of these points. So there we are. It was a fatal traffic collision. 78-year-old driver, pedestrian 71 years old got nailed, and there were a couple of passengers in the car who had no injury. So this sort of information, and if we want to get rid of the carousel, we can just simply click on that tab there. But we have another version, as I said, that has the actual model from York in here. So this, I think, provides us with a great basis for the ISUM work. Yeah. So I'm happy to answer any questions. We don't have time for the videos, but the UW one's really very interesting. It's day and night. And York fly-through is a little less interesting, but still quite impressive.
First, let's thank Brent for... Let me say that the York fly-through is working on my laptop, so I'll plug my laptop in, and then while you're answering questions, maybe we
Okay, sure, great. So does anyone have anything they want to fire at me now or at the break? Happy to answer any questions. No questions. Yep, good.
How do you convert from having data about scenery and buildings and whatever to where the roads actually are? What are the roads and indoor, the pathways and the hallways?
Well, the nice thing about moving the CAD data and all of the other data into the GIS environment, everything is geo-registered in real-world coordinate space. So once you know where a tree point is with the XY coordinate of the tree, which is in a real-world projection rather than just a random, with a 0, 0 base and a point on a 0, 0 infinity plane. You know exactly where that tree is individually, but you also know, because everything else is geo-registered, what's around it. So if we're interested in a particular tree on campus that's causing issues with respect to shade falling across something, then we could find out what features are affected by the shade that's generated by the tree, depending on sun angle, and do something about the tree.
Yeah.
So everything that's in this model is converted from table coordinates or computer coordinates to real-world coordinates, and that allows us to be able to integrate everything together within a common coordinate space.
So those models contain information on what objects are. So it
They do.
says here's something and that's a tree. Here's something that's
It's not only a tree; it's an ash tree.
right.
Or
Okay.
it's a cedar tree. And in City Engine, we have three-dimensional models for about 200 or 300 different tree species. So we can actually model locate the tree not only according to what type of tree it is, but what height it is, when it was planted, when it was last maintained or trimmed by anybody. There's a rich database sits behind every single feature. And in the BIM models, the information's extensive. It's incredible, because every item in a BIM model carries attributes with it. The lux on the type of lights that are in rooms. So,
yeah. Thank you.
yeah, it provides us with a great environment to model in. Yeah.
I was just wondering how difficult it was to use different types of files in different software, how difficult it was to convert from ArcGIS.
That's a good question. It wasn't easy, let me put it that way. There was a lot of experimentation involved. We're just flying through the York model now. And maybe if we can just dim the lights. There was a lot of experimentation involved, but virtually every software environment has export formats that can be read by other packages.
Okay.
And where we didn't have a out-of-the-box export functionality, we relied on a piece of software that's a really great tool, if you've never used it, called FME, produced by a company called Safe Software. And that provides you with translators of just about any format you could poke a stick at to every other format. So the company is called FME and the product is Safe Software. And I don't know whether it's site licensed here at York. Yeah. But we have an extension with Esri software called Interoperability extension for ArcGIS, and that allows us to move between formats pretty transparently.
Okay.
I don't know whether that answers that or not,
Yeah.
but it's.
So you talked about adding texture onto your three-dimensional models later. How are you planning on collecting that data, or is it already available to you?
We don't have any textures on the buildings at the moment. That's a good question, and that's the most difficult part of the whole process.
Possibly crowdsourcing or?
We could do that. We could simply texture these buildings using out-of-the-box City Engine textures that wouldn't necessarily reflect exactly what's on the building, but it would be a close facsimile to it. One thing we hope to do is to build a library of textures that could be crowdsourced. So somebody can take a photograph of the side of a building and upload it to this library on GitHub. And if somebody wants a texture type, they can take the texture and apply it to whatever they want to use it to. One of the good things about getting the model out of City Engine into Unity is the texturing rendering within Unity is much richer than it is within City Engine as a tool for building things, not for texturing them. So in Unity, you can texture water and grass and terrain much more realistically than you can in any other environment that I'm aware of.